Hi, everybody. We are off to chapter 3, the chapter on probability. This ends up being one of the more difficult um, topics in this course. So we're going to start with some definitions. First of all, probability is the measure associated with how certain we are of the outcomes of a particular experiment or activity. An experiment is a planned operation that carried out under controlled conditions. If the result is not predetermined, it is a chance experiment. An outcome is a result of the experiment. The sample space is the set of all possible outcomes, and an event is any combination of outcomes. So let's do an example and point out these definitions as we're going through the example. So the experiment is rolling a six-sided die. So the sample space is going to be what can happen. We could roll a 1, a 2, a 3, a 4, a 5, or a 6. So that's the sample space. We'll call it S. We can define several events based on this sample space. For example, if the event is rolling an even number, then the event E is going to be a 2, a 4, or a 6. P of A, that's kind of function notation back in your Algebra 2 days, or Math 95 days. P of A means the probability event A will occur. So the formula for P of A is P of A equals N of A over N of S. N of A is the number of ways A can happen. N of S is the number of elements in the sample space. So in our example, if I want to find out the event, I used A instead of E in this, but if A is the event of rolling an even number, then the number of times an even number can happen is 3. The total number of things in the sample space is 6, so the probability is going to be 1/2. Note that the probability of an event is always between 0 and 1 inclusive. 0 meaning it can't happen, like rolling a 7 on a six-sided die. Can't happen. All right? And it can't be bigger than 1 either. So if I say the event is rolling a 1, 2, 3, 4, 5, or 6, then you're definitely going to roll one of those. So if the probability of that event would be exactly 1. The law of large numbers tells us that if we roll a die more and more times, we expect the number of even rolls to be half the total number of rolls. So a relative frequency, like if I rolled a six-sided die, say 20 times, there's a really good chance I'm not going to get exactly 10 even numbers. I'd get a different relative frequency than the theoretical probability of 1/2. But more and more times you roll the die, the closer and closer that relative frequency is going to get to the theoretical probability. Right, part of the confusing part of probability is the or versus and. So, suppose A is 1, 2, 3, 4, 5, and B is 4, 5, 6, 7, 8. A or B is the set of elements in A or B or both, because 4 and 5 are in A and they're in B, so they're in A or B. Okay, so A or B is going to be the set 1, 2, 3, 4, 5, 6, 7, 8. A and B, the elements have to be in both A and in B, so A and B only has 4 and 5 in it. The complement of A, notated with an A, the little hash mark up above, we call that A prime, is the set of all elements in the sample space S that are not in A. So for example, if I give you that set A is 3, 4, 5, and the sample space is 1, 2, 3, 4, 5, 6, 7, then A complement is going to be everything that's in S that is not in A. So the 1, the 2, the 6, and the 7. Remember that if I go fast and you want to take your time through this, you utilize that pause button whenever you get a chance, especially if you're copying notes down while I'm talking. All right, note that in this example, the probability of A is 3/7, and the probability of A complement is 4/7. Those probabilities of A plus A complement is always equal to 1. All right, a more useful way is that the probability of A complement is 1 minus the probability of A. That's going to come in handy later on. Because what if I ask you, what's the probability that you pick at least one green M&M out of a bag? So it's going to be much easier to calculate the probability of picking 0 green M&Ms. And then you could just take that probability, subtract it from 1. Then you'd have the probability of at least one green M&M. Alrighty? Conditional probability. That this notation, probability with an A vertical bar B, means the probability that A happens given that B has already happened. All right, so the formula, and I urge you to please use these formulas. Probability of A given B is the probability that both A and B happen, divided by the probability that B happens. Or the number of ways A and B can happen over the number of ways B can happen. So, for example, if S is 1, 2, 3, 4, 5, and 6, and A is 1, 2, 3, B is 2, 3, 4, 5, then probability of A given B be the number of elements in A and B, which is 2, because 2 and 3 are both in A and B, over the number of elements in B, which is 4. So you'd end up with a probability of 1/2, 2 over 4. All right, let's go and do an example from the beginning. A ball is drawn randomly from a jar that contains 8 red balls, 9 white balls, and 6 yellow balls. Find the probability of the given event and show your answers rounded to 4 decimal places when possible. Looks like I just left them in fraction form. So, probability you get a red is just going to be the number of red balls over the number in the sample space. So you got 8 red, 8 plus 9 plus 6 is 23, so there's 23 balls altogether. Probability you pick a red ball is going to be 8/23. Probability you pick a white ball, there's 9 white balls out of 23, so 9/23. Probability you pick a yellow or a red, well, there's 14 balls that are either yellow or red out of 23, so 14/23 would be the probability of yellow or red. For a pair of dice problems, it's useful to write the sample space as a table. So you got die 1, let's say, is going down, 1, 2, 3, 4, 5, 6 going down, die 2 is going across, and then the sums, right, if you look at it, the sum 1 plus 1 here is 2. Right? You got 1 plus 2 is 3. Okay? You got over here 5 plus 4 is 9. So that's what's going on there, okay? So there are 36 elements when you roll a pair of dice. What's the probability you roll a 7? Well, here are my 7s, right? There's 6 of them out of 36 total in the sample space, so 1 over 6. What's the probability you roll a 3 or an 11? So 2 3s, 2 11s, so 4 out of 36 reduces to 1/9. Probability you roll a 9 given that you've rolled an odd number already. So that's going to be number of ways you can get a 9 and an odd. So there's 4 9s. 9 is an odd number, so there's 4 odd 9s. And how many odds are there? So 2, 3, 4, 5, 6, plus 6 is 12, 16, 18 odd numbers. So that's what goes in the denominator. 4/18 reduces to 2/9. All right, so that's a fun little problem. Independent versus mutually exclusive. Independent is a difficult concept. Two events are independent if the knowledge that one occurred does not affect the chance the other occurs. So mathematically speaking, A and B are independent if probability of A given B is the same as probability of A, probability of B given A is the same as probability of B, probability of A and B is the probabilities multiplied together. You only need to show one of those two events are independent, okay? So, with replacement versus without replacement. With replacement example. 5 white, 6 red, 7 green marbles in a bag. You choose one, put it back, choose another. So what's the probability you pick a white on the first one and a red on the second one? 5/18 times 6/18. Those two are independent because we replaced the marbles. When you don't replace it, then it depends on what you chose the first one, right? The probability changes in the second one. So without replacement, probability you get a white then a red. You have 18 marbles on your first choice. You pick a white one out, you throw it away. You only have 17 marbles left, 6 of them are red. So 5/18 times 6/17 would be that probability. Alrighty. The with replacement demonstrates independent events since it didn't matter what you chose with the first pick. It won't affect what is possible on the second pick. The without replacement example shows 2 dependent events. The second choice possibilities are affected by what was pulled out first. Alrighty. A and B are mutually exclusive if they cannot occur at the same time. All right. For instance, if I have the sample space is 1, 2, 3, 4, 5, and 6. A is the event of 3, 6. B is the event of 1, 2, 4. Probability of A and B, that's the number of A and B over the number of S. A and B can't happen at the same time because they don't share any common elements. So you get a 0. So in that case, A and B are mutually exclusive. In the second case, if A is 3, 6 and B is 2, 4, 6, 6 is common to both, so they're not mutually exclusive. All right. And formula for 2 events that are mutually exclusive, probability of A or B is just going to be probability of A plus probability of B. That's only if they are mutually exclusive. If they aren't mutually exclusive, then you're going to have to subtract off the probability of A and B. We get to that a little bit later. All right, U and V are mutually exclusive events. Probability of U is 0.23, probability of V is 0.53. Find probability of U and V. Well, since they're mutually exclusive, boom, by definition, they can't happen at the same time. Probability U and V, therefore, is 0. The second one looks like UIV, but it's a conditional probability, probability of U given V. If I use the formula, that's probability of U and V over probability of V. So that probability is also 0, since the numerator is 0. And then since they're mutually exclusive, to do the OR, I just add up the 2 probabilities and I get a 0.76. All right, next example. Suppose you have 4 green cards and 5 yellow cards. The cards are well shuffled. You randomly draw 2 cards without replacement. G1 is the first card drawn is green. G2 is the second card drawn is green. We're not going to replace the cards. All right, so probability of G1 and G2. 4/9 probability you draw a green one on the first draw. Now there's only 8 cards left, of which 3 of them are green, so 3/8 on the second pick. So 4/9 times 3/8 reduces to 1/6. Probability of at least 1 green is going to be, I'm going to use that complement thing. So it's going to be either 1 green or 2 greens. It's going to be easier to calculate no greens and subtract from 1. So that's what I do there. 1 minus 5/9 times 4/8, and I end up getting 13/18. Probability of G2 given G1. So probability of G2 and G1, we calculated in part A to be 1/6. Probability of G1, that is the probability of drawing a green one on the first draw, so that's 4/9. So I do the calculations. So probability I draw a green card on the second draw, given I have already drawn a green card on the first draw, is 3/8. All right. So they are not independent because those 2 probabilities of G2 given G1 does not equal probability of G2. All right. It looks like they are, but they're not. Let's describe why with this tree diagram. So these are often useful when doing problems like this. So first pick, green 4 nights, yellow 5 nights. Remember, we didn't replace, and now there's only 3 greens left on the second pick. So 3/8 chance you pick a green on the second pick, 5/8 chance you draw a yellow on the second pick. And then the upside down U there means and. So probability you draw a green then and a green. 4 nights times 3/8. You just multiply along the tree and you come up with 1/6. That's the probability of 2 greens. A green then a yellow is 5/18. A yellow then a green is 5/18. And then 2 yellows is 5/18. All right. So notice probability that you draw a green one on the second one is going to be these 2 guys added together. So 4 nights is actually the probability you draw a green one on the second night. That is on the second draw. So that is not equal to 4 nights. I mean, that is not equal to 3/8. So therefore, we don't have independence. All right. A student goes to the library. B, student checks out a book. D, student checks out a DVD. So the probability the student checks out a book is 0.4. Probability that a student checks out a DVD is 0.3. Probability they check out both is 0.2. So now I can do some probabilities. The conditional probability of B given D would be probability of B and D, which we know is 0.2, right? 0.2. Probability of D is 0.3. So we get a 2/3 probability that the student checks out a book given that he has checked out a DVD. All right. The opposite way, probability is somebody checks out a DVD given that they've checked out a book, be 0.2 over 0.4, which is 1/2. B and D are not independent since probability of B given D, 2/3, does not equal probability of D, 0.3. All right, so those are not independent. They're not mutually exclusive because students do check out both. The probability of B and D is not 0, so they can't be mutually exclusive. That brings us to one more rule, the addition rule. Okay, so if the 2 events aren't mutually exclusive, then you have to use this rule. Probability of A or B. I totally did not do this one correctly. This right here should be and. All right, that should be and. So probability of A or B is probability of A plus probability of B minus the probability of A and B. Helen plays basketball. C is the event she makes her first free throw. Probability of C is 0.75. Probability of D is 0.75. Did I say 0.5? 0.75 for both. And probability she makes the second one, given that she made the first one, is 0.85. So she's got that good visualization. She's going to make it. So probability of C and D is the same as probability of D and C. So probability of D given C was probability of D and C over probability of C. We have that formula from back a couple pages ago. So the left side's 0.85. So we're looking for the top here. Probability of D and C. Probability of C is 0.75. So 0.6375 is going to be the probability she makes both free throws. So then probability of C or D, probability she makes one of the 2 free throws. We add probability of C plus probability of D. Subtract off the probability that she makes both. So probability she makes one of the 2 is 0.8625. Are they independent? Heck no. Probability of D given C doesn't equal probability of D, so they're not independent. All right. A contingency table provides a way to portray data in a way that makes probabilities easier to calculate. Giving a test to a group of students, the grades and gender are summarized below around your answers to 4 decimal places. So we have 37 male students, 4 got A's, 15 got B's, 18 got C's, 27 female students, 5 got A's, 2 got B's, 20 got C's. So total 9 A's, 17 B's, and 38 C's. If one student is chosen at random, find the probability the student got an A. So that's 9 over 64. Find the probability the student was female and got a C. So there's 20 female C's over 64, so 5/16. Find the probability that the student was male or got a B. So let's look at that one. Probability of male or B, that's the number of male or B. So there's 4, 15, 18, so 37 males, and then 2 females that got B's, so we have to consider them. They're male or got a B. So I add those together, I got 39. 64 is going to be the probability of a randomly selected person being male or having received a B. If one student is chosen at random, find the probability that the student was female given they got a B. So I'm going to use my formula. Number of female B's, that's 2, over the number of B's, 17. We already know that student got a B. So now there's only 17 total of them, of which 2 are females, so 2/17. Okay, last one. According to Master Foods, the company that manufactures M&Ms, 12% of peanut M&Ms are brown, 15% are yellow, 12% are red, 20 blah, blah, blah. So compute the probability that a randomly selected M&M is not yellow. So what I'm going to do is I'm going to calculate the probability it is yellow and subtract it from 1. Probability it is yellow is 15%, so I just do 1 minus 0.15, so 85% chance that you're going to pick a non-yellow M&M. What's the probability you select a blue one or a green one? Those are mutually exclusive. You can't choose a blue and a green at the same time, so you're just going to add those two probabilities together. 23% blue, 15% green, add them up, it's a 38% chance, 0.38 chance you get a blue or a green. Probability you pick a red and then another red. So those are, we're going to assume they're independent events because we just have a whole boatload of M&Ms, so 12% chance you choose a red one on the first one, 12% chance on the second one, multiply them together, you get 1.44% or 0.0144. If you randomly select 3 peanut M&Ms, compute the probability that none of them is yellow. Well, 85% chance it's not yellow, so we just multiply that by itself 3 times, and you get 0.614125. So that's the probability you get no yellow in 3 draws, right? At least one yellow is the complement to no yellows. So for part E, when it says what's the probability that at least one of them is yellow, take your answer for part D and subtract it from 1. So probability at least one yellow is 1 minus the probability that there's no yellow. So 1 minus 0.614125, 0.385875. And there you go. Probability in a nutshell. Please do not hesitate to ask questions on this assignment. This one's going to seem, the level of difficulty is definitely ramped up in this chapter compared to chapters 1 and 2. So please do not hesitate to ask questions. There it is. We'll see you in chapter 4.